Alright, so today we will do review on function of multiple variables. Okay. So let's make a picture first about the whole chapter, and then we solve practice problem from the practice exam. And in this practice exam, you have a lot of, I think about 8 to 10 problems on this chapter. So we need to work maybe in 2 lectures. But first, let's talk about functions of multiple variables, right? So when you have function, you need to consider the domain, right? This is the first thing. I want to make a picture in here. So the first thing you need to consider is the domain. And then from calculus 1, you know, we need to consider limits, right? So after the domain, we are interested in if the function has limit or not at some point. So I have limit. Again, let me write x is equal to fxy. So just, you know, there's no difference, right? No difference between function of 2 or 3 in general idea. So limit. Let's say, what is the limit? So I write in this form, okay? Limit of x goes to x0 equal to L. So L is the number, x is the point or pair of numbers, okay? Or triple, whatever you want, right? If you consider a function of 3 variables. So x is triple if you consider such function. So x is just xy, right? And x approaches x0. x0 is a fixed one. X can approach x0 differently. You know, if we consider on the plane, so the neighborhood would be a region, right? So you see, in R1, the neighborhood is just an interval, small interval, open interval in R1. In R2, I mean function of 2 variables, right? Your neighborhood is a region. In R3, your neighborhood would be a solid region, right? In space. Make sense? So basically, you know, we have definition of sphere in 1-dimensional space, 2-dimensional space, 3-dimensional space, whatever we want. Okay? And after that, we consider continuity. So continuity, like in calculus 1, the function is continuous at some point. If the limit is and equal to the function value, right? So I write in short in here, if the limit is x and then equal to f of x0. This is a point, okay? Don't forget about it. I just write in short. So I think it's very difficult to check, you know, if function has limit, or check continuity of function by using definition. So we experience about it, right? Have some function and we have to use definition to check that. Sometimes this is extremely difficult. And after continuity, we consider differentiability, right? Differentiability. And here is the big difference between calculus 1 and calculus 3. So what is the difference? In calculus 1, we have first derivative, second derivative, right? In here, we don't have that first and second, but we have partial, some kind of that, right? Partial derivatives of the first order or the second order. So we have partial derivative. Partial derivative. Okay, what else? Partial, we have first and second, right? Okay. First and second. So we use the first derivative to find critical points, right? Like in calculus 1. So critical point. What are critical points?
where the graph changes.
Change what?
So
The partial derivatives are 0 or don't exist.
Yes. 0 or does not exist, right? So like in calculus 1, right? In calculus 1 we also have that critical point, partial derivative equal to 0 or one of them, right? Does not exist. Okay, does not exist. That's critical point. Okay, and we use okay. Let's determine what happens if x and fy equal to 0. So in this chapter we study slope, right, in x and y direction. Do you remember that? Slope in x and y direction. So let's remind you about that picture, right? So if in x direction means we have x or y, x, for example, this is x-axis, right? And you have a plane like this, right? Along x-axis, okay? And then, you know, this plane intersect with the surface by some curve, right? And we consider the tangent line to that curve. So that is called, you know, the slope of that tangent line is called, you know, the slope in x direction, right? Similarly, we have in y direction, and we have directional derivative. Do you remember that? We have directional derivative, almost the same. So, if fx equal to fy equal to 0, means, you know, the slopes in x and y directions are 0. What does it mean? That means at that point, the function may have local maximum or local minimum, right? And at least, you know, the tangent plane at that point is parallel to x or y plane. Or in calculus 1, you know, when the first derivative equal to 0, right? The tangent line is horizontal. In this case, we have tangent plane. Make sense? So, and then in here, you know, we have some kind of, yeah, first, second derivative does not exist. Maybe when you have radical function and you take derivative, you know, you convert that radical, and in your derivative, you have radical in the denominator. And in that case, you know, the function may be defined, but, you know, the derivative might not exist. Make sense? At those in special points. All right, so just very quick, how about the second one? The second derivative, we have, if we consider function of two variables, so we have different kinds of partial second derivatives, right? So we have x, y, y, x, and y, y. Is that correct? So you have x, and here you have x, y, and you have y, x, you have y, y, right? Y, y. Basically, you know, if we consider this determinant, and in our course we suppose that fxy and fyx are equal, our function is good one, right? If our function is good one, so we have this condition. We are not very strict on that, and once we calculate this determinant, right, at some given point, and again, I have to remind you about this, because on the test, we have one problem, and you need to classify critical points. Do you remember that? So we might have local maximum, local minimum, and saddle points, right? Saddle points. So, you know, and those points should be at one of critical points. Don't forget about it. First, there should be critical points, right? And then you calculate second partial derivatives, and you know, calculate this determinant. Okay? You have to plug those critical points into this. I remember many of you just, you know, calculate this without solving these equations or considering this case. So and when you calculate second derivative right away, right, you find determinant and you get some equation, some expression of x and y. So how to do with that? We cannot, right? We might have that, but first we have to find all critical points and then plug those critical points into this determinant, right? Into this determinant, and you see. So we have several cases here. If you have, if d is less than 0, you have saddle point, right? If d is greater than 0 and fxx greater than 0, you have minimum, right? And if d greater than 0 and fxx less than 0, you have maximum. Get it? So that is very, similar to calculus 1. So that is second derivative test. Okay, the second derivative test. All right. When we're talking about differentiability, we need to talk about gradient. Gradient. That is very big difference, right, with calculus 1, right? So what is gradient? That is just vector of partial derivatives, right? Partial derivative. And we use, we use gradient a lot. Now try to recover those applications, okay, together. So of course this is a vector of partial derivative. But I remember we saw one problem about heat-seeking. Do you remember that? Heat-seeking particle. And that particle, if that particle moves along the direction of increasing, right? So we each time that that move along the direction of gradient, right? Because the gradient is what? Is the direction of maximum increase, right? Forgot? So gradient is the direction of maximum increase. And if you take normal of that, right? You take normal of that, so you have the the maximum decrease. So the opposite will be the direction of minimum or maximum decrease. Let's see that, right? Agree? So that is the significant meaning of the gradient. Okay, so we know that if we have function of 2, 3 variables, we need to use. Do you see him? Okay. If we have function of 2 variables, right, we can describe the surface using level curves. Right, using level curves. That means we have to set this function equal to c, and for different c, we have different level curves. Or finally, you come.
Yeah. I have to.
You don't have to.
Bro, we got exam on Monday.
Today I will do review on our chapter, not on the test. I'm kidding. Anyway, level curves, right? So we have different level curves. We can describe that, right? And gradient vector is very important because gradient vector is perpendicular to all level curves. Imagine you have surface in 3-dimensional space, right? But level curves are in 2-dimensional space. Make sense? So this gradient vector is in R2, right? So that is perpendicular to all level curves in here. So that's why when you consider problem heat-seeking particle, that move along this, right, perpendicular to that, because that direction is the direction of maximum increase. All right. So what else about gradient? I think in reflection journal I asked you 3 questions, right? One of those is 3 applications of gradient. Do you remember that?
I remember doing it.
But now you don't remember your answer.
I forgot to submit it.
You get 0 for that. It's easy. All right. So we use gradient to find what? And based on the properties that gradient is perpendicular to level curves, right? So if you consider function of 3 variables, you will not have level curves, but you have level surface, right? And using that, gradient vector is, you know, perpendicular to level surface. You can use that to find the plane, the tangent plane, right? The equation of tangent plane. And then gradient in this case is the normal vector of the tangent plane. Is that correct? Tangent plane. So we use that, don't forget. So we can use gradient to find tangent plane, because that is normal vector, right? We can find that is, you know, direction of maximum increase. What else? And we can use gradient to find angle of inclination. But you know, that is easy. That is easy because, you know, we have tangent, we have normal vector, and then once we have normal vector of that plane, and then, you know, in order to find the angle of inclination, we just find the angle between that vector, the normal vector, and then the k, right? The z, a6. So that is k001. So that's not a big deal. But anyway, you have formulas with you. I will not remind those formulas, okay? After this gradient, we study what? Total differential. Total differential. We study total differential function, and we use total differential to approximate the change of the function, right? Approximate the change. So total is dz equal to fx dx plus fy dy. Or sometimes, you know, we just write, yeah, that is just gradient dot product with dx dy. Right? Gradient dx dy. Just dot product. And you know, this formula reminds you about the differentiability of function of two variables. Differentiability of function of two variables. So what's that? That means if your function can be represented in the form, you know, differential plus sigma delta x plus sigma 1 delta x plus epsilon 1, epsilon 2 delta x delta y. Do you know that? Where epsilon 1 and epsilon 2 are very small, right? So that is some kind of generalization of that from calculus 1. But using that, you know, we can use this to approximate delta z, the change of the function. If you have very complicated function, we may use differential to approximate it. And this is what, you know, we also consider in calculus 1. It's not something special, but that is useful. Okay? And after this, we use all these things, the first partial derivative, second partial derivative, gradient, etc., to consider some optimization problems, right? Optimization problem. Maximum, minimum, I'll write here. Optimization problem. So, yeah, we have, in this chapter, we consider some problems like, first we consider optimization problem inside the region, right? Inside the domain. Do you remember that? If we consider such problem inside the domain, without boundary, let's say that, without boundary. If you consider inside the domain, so you have to do all this then. You have to find the first partial derivative, right? And then, you know, find all critical points. Like in calculus 1, right? Find all critical points, and then you might use second derivative test to test if that is extrema. Do you remember that? So all those things, you know, is similar to calculus 1. But the problem is, you know, in calculus 1, you consider interval, and you have only 2 endpoints, right? That's good. You consider only 2 endpoints. So if you want, you can compare function values at 2 endpoints, right? And you pick the maximum, minimum between them. But if you have function of 2 variables, so your region looks like this, and the boundary is a curve, right? So you have infinitely many points over there. And if you have that problem, how to optimize, right, your function with some constraints, right? This is called constraint because we consider only on this curve. Make sense? So in that case, you have to do, remember, Lagrange multiply. The main idea of that is, if you have some function, right, and you need to optimize that, and here the constant, is given by some equation, right, by some equation, and so your function attains maximum or minimum if and only if the gradient vector of the given function is perpendicular to this. Get it? It is perpendicular to this. If the gradient is perpendicular to this, means the gradient vector of the constant, is scalar multiple of that. Get it? So you have on the boundary, you need to do f equal to lambda g. That is application. Of course, we have multiple applications of function of several variables, but we just consider that. And for this approach, I remember we consider like the least squares problems, right? I think that is all about this chapter. So we have the whole picture about this. Basically, when we study this chapter, I said that this is some kind of generalization of calculus 1. So we consider most of questions from calculus 1 for function of 2, 3 variables, right? But we have some specific objects like gradient, right? Tangent plane, direction, or differential sometimes, something like it, and then here is the Lagrange multiplier method. Okay, so I hope you recover a little bit about this chapter. Now we move to practice problems. Okay, do you have any questions on this? You good? All right, let me erase this. So I think we need to spend 2 lectures on this. And we'll see, how many minutes you would need for this practice exam. So the first problem, find the range and the domain of the function. You have function f equal to 25 minus x squared minus y squared. You have to find the domain. So the domain of this function is not difficult because you have square root, right? Once you have square root, everything under the square root should be non-negative, right? And that is your condition. So you have 25 minus x squared minus y squared greater than or equal to 0. And then you have x squared plus y squared less than or equal to 25. So that is the circle center at the origin, and the radius equal to 5, right? And everything inside that circle. The range, you can say all non-negative numbers. That's it. Because that is obvious, right? So you solve this problem in 1 minute. Maybe 30 seconds. The second question about the level curves and sketch level curve. I remember this problem on the test. It was so funny. I asked you to sketch straight lines, right? But only 3 or 4 got correct. So we have the function z equal to 6x squared plus y squared. And then let's say, c equal to 1, 2. We need to sketch the level curves, right? For such c. So we just put the function equal to 1 and 2, right? Let's set function equal to 1. So you have 6x squared plus y squared equal to 1. So what's that? What's that? Is this circle?
No.
Ellipse.
Ellipse. Ellipse, right? So ellipse you can write, yeah, x squared over 6 and here equal to 1/6, right? No, you just pick some ellipse. Don't have to draw that exactly, right? But you can make some kind of this. When x equal to 0, y equal to plus minus 1, right? So x equal to y plus minus 1 in here, -1 and 1 in here. When y equal to 0, x equal to plus minus square root of 1/6, right? Square root of 1/6 less than 1, so square root of 1/6 is around this. Is this? So you get ellipse. And this is for c equal to 1. Get it? So for c equal to 2, you would get something like that. Agree? So you can solve this in 2 minutes. Can you?
Not really. I gotta read more.
All right, next problem. Find the limit if it exists. The limit, let's see, if we have enough time for that. And then z, x, y minus z, and then I can write, in short, x goes to -1, 2, and 3. Okay, x goes to -1, 2, and 3. Is it good? Okay. So the limit, the worst case is this. You plug the number, right, the point into the function and you get 0, 0, some kind of undetermined, right, form. But you plug this guy into this function, you get what? Here you have x, y, x equal to -1, y equal to 2, and then -3. So this number is different to 0. You are good, right? So just plug the number into that. You need just 30 seconds to solve this. Make sense? I don't ask you to test the limit or continuity, you know, just plug numbers into that. And that is what? That is ln 3 over 91 times 2 minus 3 and whatever you get. So you should not complain about it. Oh, the second part of this is discuss the continuity. Discuss the continuity of this function. Okay? So this is more difficult a bit. The function is defined. So in order to discuss about continuity, we need to find the domain first. Right? What is the domain of this function?
Xy is not equal to z.
What?
Xy should not be equals to g.
Yes, z is not xy. So we exclude all points on the surface z equal to xy. That's the first. What else?
Z should not be
Z should be greater than 0, right? Z should be greater than 0. Okay? So except those points, the function is continuous. That's it. So basically this question is equivalent to the question determine the domain of that function. Make sense? Okay? So, you know, I don't see any problem with this. All right. Now let's move to differentiation. Find all first partial derivatives. And your function is f of x. Okay, I write in short, fx is equal to x squared plus y minus z squared, and they give you the point -9, -9, 1. Yeah, you have to find all first partial derivatives at that given point, right? So basically you have to find fx, fy, fz. So in this case we use the chain rule, right? We use the chain rule. Please tell me, what is partial derivative with respect to the x? Tell me real quick. 1/2? No, I don't need. Just x over square root, right? Just, that's it. You copy everything and put in here. Partial derivative of y is what? Now we need 1/2, right? So 1/2 square root, right? Okay. And then what's the next? Negative z over square root. And then you plug number, all these, three numbers into those formulas to get your answer. So you would need about just writing and computing 2 minutes for this, or maybe 1.5. Okay. Next question, find the slopes of the surface in x and y directions at some point. So you have surface z equal to x squared ln y plus 1, and the point is 700. You need to find slopes in x direction and y direction, so we know that, right? Slopes in x and y directions are just partial, just partial derivative, right? So you just find zx, zy, and then you plug 700 into that, 700 into that, and you get your answer. Make sense? Again, differentiation rule. Okay, let's do one, right? So partial derivative with respect to the x. So here we don't have x in here. That's good, right? So that function is nice. So I just have 2x ln y plus 1. Is that correct?
Okay.
And then you plug x and y into this function. You get slopes in x direction.
Yeah. Okay. Yeah, that sounds good.
All right.
Yeah, I know.
Next question, find the total differential.
Yes, ma'am.
Total differential w equal to 4xy squared minus 2x cubed y squared. So basically, you have to find partial derivatives, right? With respect to the x and y. Do you need me to solve that? No. No, okay? No. No need. Just copy that. And the next question is about the chain rule. Okay? I repeat again, right?
Is that the problem where you have to do the curly D?
No, yes, no. But the chain rule is different one. For this guy, total differential, that means you have to find dw equal to wx dx plus wy dy.
Okay.
And here's what you asked. So chain rule. Okay, I remind you again, right? Don't use wrong formulas. Okay. Derivative and partial derivatives are different, right? So basically, if you have some function w equal to f x and y, and then x and y are function of, for example, rt or something like this, right? Rt. Okay, so when we need to find partial derivatives of this guy with respect to the r or t, we need to use the chain rule. We need to use the chain rule. So the formula is what? Let's say w with respect to the r is what? Now
Derivative of w with respect to that.
w with respect to the x, and then I can write x with respect to the
R.
r, right? You can write it. Or you can write, let's say w with respect to the y, and then dy with respect to the r, right? I mean, I just write in different forms, so. And your job is just apply differentiation rule. So I don't think we need to do that. Do you need? All right. The next problem is the implicit differentiation. So you have function y, given by the following. Oh man, I chose a very bad function in here. It's not a good one. But anyway, let's solve that. Let's add z to this, z squared, and then xy plus xz equal to 4. Let's change a little bit, right? Make it more complicated. Because the function in practice exam is just function of one variable. So if you have this function, so function z, right, depending on x and y and z, is given implicitly by this expression. So they ask you to find z, partial derivative with respect to the x, and partial derivative with respect to the y. So if you don't remember the formula, you can use the chain rule, right? In case if you don't remember the formula, but you should have that. So what is the partial derivative of z with respect to the x?
Is it partial derivative of x over negative partial derivative of z?
Let's say negative in here. And then the whole function with respect to the x over fz and negative fy fz, right? Fz in here. So what is f? F is the whole function in here, right? Or in this example, you can just cross multiply, and then you have a polynomial. It's easier. You don't need to work with rational, right? Just multiply, for example, xy squared z squared equal to 4xy plus 4xz, and then you bring everything into one side, right? Then you put your function f x